we'll get going then with chapter 6. So chapter 6 is going to be all about chemical composition. So again, I've mentioned this a couple times, but we have these sort of like stacks of concepts that we're building. We're still working, I guess, sort of on the second stack where we've talked about atoms, what atoms are made of, talked about how atoms can combine into molecules or compounds, and then also how those compounds can combine into different things. We've covered atomic mass is the average of all the masses of the isotopes. Oh shoot, there's another one. Oh, we've talked about sort of chemical changes as well, where we're changing the exact proportions. Oh, this was the one I was thinking of. Conservation of mass, right? Or conservation of those atoms. Whenever we go through a chemical process, the atoms that you start with are going to, there's going to be the same number of atoms that you started with, that you end with in any chemical process, but they're going to be rearranged. So that's kind of, we're building on that here now. So sodium is an important dietary mineral. It's one that's very, very easy to get. And it's in table salt, right? It's sodium chloride. So sodium is involved in the regulation of body fluids, and eating too much of it can lead to high blood pressure, which is due to osmotic pressure, which might be at the end of this chapter. Oh, no, that's chapter 15. Essentially, if you have too much salt in your blood, it draws water out of your cells, which increases your blood pressure. The chemical composition of sodium chloride, which we've looked at it several times now, is sodium and chlorine. We've talked about how to name these things, right? So there's one sodium ion to every chloride ion, because it's the ion of chlorine. So it's an ionic compound. Since the masses of sodium and chlorine are different, the relationship between the mass of sodium and the mass of sodium chloride is not clear from the formula alone. So the relationship between the masses of sodium and the masses of chlorine is not 1-to-1. Right? We can't say that if we had 10 grams of sodium chloride, we would not have, right, equals the slashes does not equal 5 grams of sodium plus 5 grams of chlorine. We don't know how much it is. We'll get to how you can calculate it later. So we need to calculate the amount of a constituent element in a given amount of a compound. And that'll be dependent on its mass, or its formula mass. Is everybody done with the slide? I am trying to slow things down a little bit. I know I go fast. All right. So the amount of element in a compound can be calculated using the chemical formula along with the masses, right? So we had the formula mass, or we can use the atomic masses to get the formula mass. So let's say this mining company needs to know how much iron is in a given amount of iron ore, right? So for every rock that they pull out of the mountain, how much of that rock is actually iron and how much of it is other stuff? Because there's always other stuff. Or if you're estimating the threat of ozone depletion, requires knowing the amount of chlorine in a given amount of chlorofluorocarbon, which is a refrigerant that's not used anymore. You might hear old people complaining about car AC not being as cold as it used to be. It's because we don't use Freon anymore. It destroys the ozone. So if you want to know how much of these, how much of the, maybe dangerous component of a chemical is present or is in a certain amount of mass, or if you want to know the amount of iron, you need to be able to count those individual atoms, really. And because we can't actually count individual atoms, we can do it sort of by proxy, kind of do it in a roundabout way. An analogy for this would be selling nails by the pound. So if you need, hundreds of nails to build a house, you're not going to go to the store and say, I want, 10,000 nails. They're not going to sit there and count them out one by one for you. They're going to say, oh, well, here's 5 pounds. It's probably more than 5 pounds. Here's 5 pounds of nails, though. That should be about 10,000. So instead of counting them, we can say one nail weighs however much. So 10 pounds of nails, 5 pounds of nails should have this many nails in it. So this is similar to our problem with how many atoms are in a given mass of an element. So if you took a bottle of water and said, how many atoms of water are in here? Well, we're not going to count all the atoms, can't do that. But we know how much a single atom weighs. So we can say that if a single atom weighs this much, and we have this much mass, then we can do the math and say that there must be this many atoms of water to create this mass. The analogy then continues that different size nails are going to weigh different amounts, right? A bigger nail is going to weigh more. So in a pound, you'll get fewer nails. So say that we have a customer. They buy 2.6 pounds, 2.60 pounds of medium nails. And a dozen nails weighs 0.150 pounds. So we can say 12 nails. Well, even better, we could say 12 medium nails weighs 0.150 pounds. So how many nails did this person buy? At this point, you should look at this and think that that looks like a conversion factor, and it is. All right, so we can do this two ways. One, we could figure out how much one nail weighs. And to do that, we could say, well, if 12 nails weighs 0.15 pounds, how much does 1 pound or one nail weigh? Yeah, divide the weight. I think that's what you said. So we take 150 or 0.150 pounds divided by 12 nails. Whoops, nails. And we'll get, let's see, what would that be? 0.150 divided by 12. Myself a little more room here. 0.0125 pounds per one nail. I'll say we can also do this the other way. We're going to figure out how many, if this is how many nails there are in 0.15 pounds, how many nails would there be in 1 pound? So you just flip this. So 12 nails in divided by 0.150 pounds. So 12 divided by 0.150 will actually give us, 80 nails. Not worrying about significant figures here yet because, well, we're not reporting an answer yet. So you can do this other way. Oh, sorry, this is nails per 1 pound, which looks more like a 1. So in your conversion factors like this, when you divide by one of those things, you're actually figuring out how many nails per 1 pound or how many pounds, nails per 1 pound or how many pounds per one nail. So we can use either of these conversion factors because actually if we flip this upside down and we do 1 divided by 80, we will get this number. So they're interchangeable.
So was it like the same answer? Did we get the same answer, or how did that work?
Yeah, so if you want to take your calculator, or here, I can do it on here too. Pull up this one. I don't like this calculator, which is why I don't use it very often. So 1, and I hit divided by 80 equals 0.0125. Oh, man.
So why would you flip that?
Did I do that? No, we don't like that. It's because the aspect ratio of the screen is weird. So it's 0.0125. Sorry, what did you say? Why would you?
Yeah, like, so why would you flip it? Why would you flip the 80?
to make it a little easier to work with, because you can use either one.
Oh, okay.
You can use either one, yeah. So, I mean, we can do this both ways. And this works for all conversion factors, by the way. If we have 2.60 pounds of medium nails, we want to convert that into how many nails we have. So we do 2.60, and then let's use the 0.125, 0.0125 pounds per one nail. Oh, sorry, I did that upside down. We have to flip this, right? Because if I put nails on the bottom, nails is the unit we want. One nail, because here we've units of pounds, so this is 0.0125. Right, that's the mass of one, or the weight of one nail. So now I do 2.60 divided by 0.0125 is 208 nails. But we could also do this as, let me make this just a little bit smaller. We could say we've got our 2.60 pounds. I'm not going to write out the whole thing. And we know that that's also 80 nails in 1 pound. So I used to do 2.6 times 80. And also gives us 208 nails. Oh.
Are those all different, different ones, or all the all same?
Sorry, what was that?
Are those like all different questions, like either different questions at the bottom?
No, so each of these is answering the same question. How many nails are there in 2.6 pounds? So as long as you have your conversion factors set up correctly, by which I mean that, right, a single nail, if 12 nails weighs this much, then one nail should weigh less than that, sort of thing. Yes, yeah, so you could set this up also as 2.60 pounds times 12 nails over 0.150 pounds. And you'll also get 208 nails. So as long as you have the correct conversion factor, and you set up the units correctly, because on each of these, notice that we have pounds, pounds. This is pounds, 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 pounds. You'll get the right answer. Which distracts a little bit from the point here, being that we can use the weight, the mass of a dozen nails, to calculate how many nails you buy in 2.6 pounds and 10 pounds and 100 pounds, it doesn't matter, based on the mass of 12 nails or 1 nail or 80 nails. So atoms are similar in that we don't want to sit around and count individual nails, don't want to count atoms. And then we have all the masses of the atoms, if this is still on the periodic table. So if you think of like medium nails versus small nails, we've got our smallest nail is hydrogen, and our largest nail down here about with oganesson. So we can use their mass and the mass per a number of nails to count them. Yeah, even if you could see atoms and counted them for 24 hours a day, as long as you lived, you would barely begin to count the number of atoms in something as small as a grain of sand, because there are just so many. Oops. So a dozen is a convenient number for nails. It's also a good number for eggs or for most things, really. But because atoms are so small, we need a much, much bigger number to count them by. So the number that we use is called the mole, abbreviated MOL. So 1 mole is this really, really big number. 6.022 times 10 to the 23. And it's also called Avogadro's number, named after Amadeo Avogadro, who did the math. Yeah. So this is the number that we're going to use throughout the rest of the semester, and if you do more chemistry throughout the rest of chemistry, to count the number of atoms. Usually we count them in moles. So 1 mole of atoms, ions, or molecules generally makes up objects of reasonable size. So if you have a mole of copper atoms, then that's about 22 pennies. So in here, there are 6.022 times 10 to the 23 copper atoms. 1 mole of helium atoms is about 2 balloons. So in each of these balloons, or in these balloons combined, I should say, there's 6.022 times 10 to the 23. I'm just going to abbreviate helium atoms. So that's why we use the mole. Because even though there's literally an unimaginable number of the atoms or molecules, this is a workable scale. So if we wanted to do the math, the numerical value of the mole is actually defined as being equal to the number of atoms in exactly 12 grams of pure carbon-12. So it's a carbon with 6 protons, 6 neutrons. And if you took this 12 grams and you divided it in half 79 times, you would get a single carbon atom. So based on this, if you have carbon-12 in 12 grams, 12 grams of carbon-12 equals 6.022 times 10 to the 23 atoms. I'll even go so far as to say atoms of carbon-12. Which one?
Where you got that carbon-12?
Oh, the carbon-12? Well, that was just this right here. Yeah, so exactly 12 grams of carbon-12 is 1 mole.
And then how'd you get the 6?
Because this is, sorry, this definition of the mole establishes, I'm on the eraser.
Oh, it's a 1 mole, right?
So it was, Avogadro did the math to say that there are this many atoms in 12 grams of carbon-12. So then we can count the number of atoms by weighing them, rather than one at a time. Okay, so if we can convert then between the moles and number of atoms, similar converting between dozens and number of nails. All right, so if you have 1 dozen nails, that's 12 nails. Easy to do that conversion. Similarly, 1 mole of something, or 1 mole of a number of atoms, is this many individual atoms. So we can take our 9.5 times 10 to the 27 atoms. We can use this conversion factor. 1 mole equals 6.022 times 10 to the 23 atoms. So because we want to cancel out the units of atoms here, we have 6.022 times 10 to the 23 atoms is 1 mole. Oops. So 9.5 e to the 27, or times 10 to the 27, divided by 6.022 times 10 to the 23 will give us 15775.49, or we should use scientific notation here because we only have 2 sig figs. This is going to be 1.6 times 10 to the 1, 2, 3, 4 moles. So it's just another special conversion factor unique to chemistry. So now we could say how many gold atoms are in a pure gold ring containing 8.83 times 10 to the negative 2 moles of gold. So 8.83 times 10 to the negative 2 moles of gold. And now we want to count, or we want to go to atoms. So if our relationship between moles and atoms is 1 mole equals 6.022 times 10 to the 23 atoms, then we want to cancel out moles. So 1 mole will go on bottom, then 6.022 times 10 to the 23 atoms on top. So it's going to be 8.83 e to the negative 2 times 6.022 e to the 23. This is going to be 5.32 times 10 to the 22 atoms of gold. So it's at this point that the E key, letter E key on your calculator is going to be super helpful because you can use it like this. So for this calculation, I typed in this. This is more of an asterisk. So the E there just takes the place of times 10 raised to, and then you put your exponent after that. Good?
And you got the 5.32 because it's sig figs and that was 5.31 and 702.
Yep.
So the E you said replaces the x times the x 10 things, right?
Yeah, so it'd be times 10 to whatever number. Any other questions? It's another conversion factor. So if you just check out the units, make sure you're canceling your units properly, you can convert between moles and atoms. All right, so if we want to figure out, going all the way back to, well, either how many atoms are in a human body or how many, how much sodium is in, or how much sodium chloride you could eat and still be under the 2.4 grams of sodium that's recommended, we need one more conversion factor between moles and grams. So for nails, we used the weight of 1 dozen nails in pounds. For atoms, we use the mass of 1 mole of atoms. So molar mass is that conversion factor. It's the mass of 1 mole of atoms of an element which is numerically equal to the atomic mass in grams. So for carbon-12, specific isotope of carbon, there are exactly 12 grams of carbon-12. Well, exactly 12 grams of carbon-12, so that's 1 mole of carbon-12 equals 12 grams of carbon-12. So the atomic mass unit is actually defined as 1/12 the mass of a carbon-12 atom. So these are the numbers that we have actually on the periodic table, right? We learned how to calculate atomic mass. It's the weighted average of all of the isotopes and their abundance. So for carbon, there are actually 2 other isotopes of carbon. There's carbon-13 and carbon-14. So our mass of carbon is 12.011. So those small amounts of carbon-13 and 14 increase that mass a little above 12. So when we talk about the molar mass of anything, we can use the atomic mass from the periodic table. Because statistically speaking, you're going to have that distribution of those isotopes in anything you're working with. So if we have 1 dozen large nails, right, that's going to weigh more than 1 dozen small nails. Just like if we have, like hydrogen has a mass, atomic mass of like 1, whereas something like lead has an atomic mass of 207. So 1 mole of lead is going to weigh a lot more, 207 times 1 mole of hydrogen. Or like this, if we have 1 mole of sulfur, will weigh about 32 grams. 1 mole of carbon, on the other hand, will only weigh 12 grams. Because the atoms, each individual atom is smaller and lighter of carbon than it is of sulfur. So for each element then, we've got a different mass. So sulfur being 32, 12 for carbon, 6.94 for lithium. So the lighter the atom, the less mass in 1 mole of that atom. Just like small nails, a dozen small nails is going to weigh less than a dozen large nails. Key takeaway being molar mass is the conversion factor between grams and moles. We're going to be using molar mass all the time for the rest of the year. Probably the most important conversion factor. So for 91.4 grams of calcium, I want to calculate how many moles of calcium. Need to get new glasses. I have a periodic table. It was 40.078. So the first thing we need to do, after writing down everything we're given and what we're trying to find, is find the molar mass of calcium. So it's 40.078 grams of calcium equals 1 mole of calcium. So all of the atomic masses on the periodic tables are in grams per mole, which is the molar mass. So if we have 91.4 grams of calcium, we now want to cancel out units of grams. So we'll put our 40.078 grams of calcium on the bottom, and that's equal to 1 mole of calcium. So 91.4 divided by 40.078 will be 2.28 moles of calcium. So it's just another conversion factor. We just now have an entire periodic table of new conversion factors. All right, so if we want to calculate the number of grams, now in 2.78 moles of sulfur, and know the number of grams. So what's our first step? Find the molar mass of sulfur. So sulfur is 32.066. That's grams of sulfur. Well, you can also, it'll also be written like this, as grams per mole of sulfur. Much more compact. Still, it's always grams there. Grams is always going to be the big number. Moles is always going to be 1 for those from the periodic table. So you do 2.78 moles of sulfur, and we want to cancel moles of sulfur. So that'll go on the bottom. 1 mole of sulfur is 32.066 grams of sulfur. So 2.78 times 32.066. And we'll get 89.1 grams of sulfur. Good so far? I think there's a whole bunch of these right now. Maybe that's next. Aha. How many carbon atoms are in 0.58 grams of diamond? Now, diamonds are made of carbon, which is kind of hinted at here in that it's asking you for how many carbon atoms are in this much diamond. So the only way you could solve this is if diamonds are made of carbon. That's trickier than any question that I'll ask on an exam. So 0.58 grams of carbon, and now we want to know how many atoms of carbon that there are. So we can start this out the same way, because really with a mass of any element, or any compound for that matter, the only way we can really go for now is moles, right? So we want to convert this grams of carbon to moles of carbon. Don't need to look up carbon. Carbon is 12.01 grams per mole. But we're going to need one more conversion factor here, and that's to go from moles then to atoms. And that's where we use Avogadro's number. Because moles is just like a dozen, right? It doesn't matter what it's a dozen of, it's always 12 of that thing. A mole of something is always 6.022 times 10 to the 23 of that thing. So in this case, atoms. So 1 mole is equal to 6.022 times 10 to the 23 atoms. So now we can start with 0.58 grams of carbon, then convert to moles of carbon, so we want to cancel grams. Then we want to cancel moles, since that's the units that we have on top here, and get to atoms. So 1 mole is 6.022 times 10 to the 23 atoms. So I do 0.58. And then it's been a while since we had a problem that had this many steps. Again, I always multiply across the top and then divide by everything that's on the bottom. So 0.58 times 6.022 e to the 23 times 10 to the 23, then divided by 12.01. So we only have 2 sig figs, so this will be 2.9 times 10 to the 22 atoms of carbon. The only time you're really going to use this Avogadro's number conversion is when the question is asking for atoms or molecules, or if you're given atoms or molecules, because then you got to go from that to moles, or get to moles so you can get to atoms. I think the next one is going to be starting with molecules. Atoms, starting with atoms. All right, so far we've been doing the problem one way. Right? So we've worked from, in the last one, from grams down to atoms. So from a bigger thing down to a smaller division. Now we're going to go from atoms to grams. So we've got to remember mass is grams. I'll always, again, just provide good examples of, like, I will tell you the units that I want the answer to be in. So I won't just say the mass of something. I'll say, give me the mass in grams of 1.2 times 10 to the 24 helium atoms. So we'll start with that. 1.23 times 10 to the 24 atoms of helium. Periodic table is nice because it has a lot of precision, but it's a lot of numbers to write. On exams, again, use the level of precision that's on the periodic table that I give you. So like this periodic table goes out to 5 decimal places for helium. I think the periodic table on the exam only goes out to 2 decimal places. So our first step here is we have atoms. We want to get to grams of helium. So we have to go from atoms to moles first, because then we can go from moles of helium to grams of helium. So the conversion factor for atoms to moles, 1 mole is 6.022 times 10 to the 23 atoms. And then the molar mass of helium, just going to use 4.00 grams per mole helium. So starting with atoms of helium, we want to cancel out atoms, so we'll divide by it. So that 6.022 times 10 to the 23 is 1 mole. And then is 4 grams per mole helium, is 4 going to go on the top or the bottom? Yeah, 4 will go on top because it's grams per mole and we want to get grams. We want to get grams and we want to cancel out moles. So this is 1 mole helium, 4.00 grams helium. We can calculate it. 1.23 e to the 24 times 4 divided by 6.022 e to the 23. So it's 8.17 grams of helium. It's like a pretty decent amount of helium. All right. Still no questions? Still good? Still just converting numbers? yes. So remember I said if you tried to count atoms like for the rest of your life, you'd get like a grain of sand. This is, if you had 22 pennies, right, that's 1 mole of copper atoms. If you had that many pennies though, not atoms of copper, but 6.022 times 10 to the 23 pennies would cover the Earth's entire surface to a depth of 300 meters. That's including the oceans. Like over the oceans technically, but like over the oceans, the entire world would just be 300 meters deep in pennies. And then if you took just a single grain of sugar, which weighs less than like 1 milligram, has a diameter of less than 0.1 millimeters, 1 mole of sugar crystals that small would cover the entire state of Texas to a depth of several feet. This would be a lot of sweet tea. But it's just like numbers that big just don't mean anything, which is why we put them into terms of moles, because we don't have to deal with that in addition to typing exponents. Do you guys know how far away the moon is from Earth? It's like 240,000 miles. That's far enough that you can fit all of the other planets in between Earth and the moon. Like if you stuck them in there edge to edge, you could fit all the other planets and have some space left over. Not the sun. You can't put the sun in there. Yeah, I mean, it's just, the size and scale of things is ridiculous. So, this is getting, wait. Oh, no, it's the next, there's part of this that gets kind of technical. So, but for elements, the molar mass is the mass of 1 mole of atoms of that element, right? So we covered that. Those are the ones on the periodic table. For compounds, the molar mass is the mass of 1 mole of molecules or formula units, right? Because it's sugar or salt, not sugar, salt. Sodium chloride is a formula unit. It actually forms more like a grid, like this. It's just the simplest piece of that grid is NaCl. So the mass of, and actually we calculated this at the end of the last chapter. That was the formula mass. Right, so we use formula units for ionic compounds. So we can convert between the mass of a compound, it's the mass of a compound, and the moles of the compound. Then we can calculate the number of molecules or formula units from moles. I think this slide's out of place. Oh yeah, this is what I was thinking. So the molar mass of a compound in grams per mole is numerically equal to the formula mass of the compound in atomic mass units. So these are atomic mass units, which are, what it means by numerically similar or numerically equal is that the numbers are equal. The concepts are different slightly. But we use them like they're the same. The formula mass for a compound is the sum of the atomic masses of all the atoms in a chemical formula. That's what we did at the end of chapter 5. So for something like calcium, or calcium nitrate here, I actually like to do it this way. You have calcium, and then remember, if we have something in parentheses, we have to multiply everything in the parentheses by the subscript outside of those parentheses. So we have the 1 calcium. We'll have nitrogen and oxygen, 1 calcium. We have 2 nitrogens and 6 oxygens. The mass of calcium, we used it earlier, was 40.78. 0.78, sorry. Mass of nitrogen is 14.01. Excuse you. The mass of oxygen is 16.00. So you take the atomic masses of each of these elements in the compound, multiply them by the number of that element in the compound. So this one will be 40.078. 14.01 times 2 is 28.02. 16.00 times 6 is 96.00. And then we'll add all of these together. So 96 plus 28.02 plus 40.078. So 164.10 because we're adding here, and then these only have 2 decimal places. So only keep 2 decimal places for our significant figures. So the formula mass is 164.10 AMU. The molar mass is 164.10 grams per mole. So they end up being the same. So this will be a process for calculating for any compound what the molar mass is. Tracking so far? Any questions? All right. Nope. No? Okay. So these end up now being very similar to the problems we did before for just individual elements, with one extra step where we need to now calculate the molar mass for a compound. So if we start out here with our 22.5 grams of CO2, and we want to find the number of moles of CO2, we need to calculate then the molar mass of CO2. So we can start by writing out all the elements that are in it: carbon, oxygen, 1 carbon and 2 oxygens, and then multiply by their atomic masses. (12.01).
Thank you.
Yeah. And then 32. So this will be 44.01, and then the units on this are grams per mole. So it's 44.01, that's the grams, and it's that many grams for 1 mole of CO2. So with that, we now have a conversion factor between grams of CO2 and moles of CO2. So we can start with our grams, 22.5 grams, and then does 44.01 go on the top or the bottom? Goes on the bottom because it's 44.01 grams. All right, so the grams here matches the grams here. This is 1 mole of CO2. So we get 22.5 divided by 44.01 for 0.511 moles CO2. Right. So we'll do this again. Now with nitrogen dioxide. So we got 1.18 grams of NO2. Have to calculate the molar mass, because again we're going from grams to moles. So we want to know how many moles nitrogen dioxide. So we have 1 nitrogen, 2 oxygens, Nitrogen is 14.01. Oxygen is 16. So 14.01 plus 32 is 46.02. Whoops, hold on. 0.01. Again, that's grams per mole nitrogen dioxide. So you get 1.18 grams NO2. So does 46.01 go on top, bottom? Bottom, yep. So you can just memorize that when you want to go from grams to moles, you divide. When you want to go from moles to grams, you would multiply. I think it's better to sort of remember the general canceling of units. But it works both ways. You'll get the same thing. So we'll now get 1.18 divided by 46.01 for 0.0256 moles NO2. Correct sig figs and all. Couple more examples, I think, because this can go both ways. Oh, no, we're not going both ways yet, but we are going one step further this time. So we've got 3.64 grams of H2O. And we want to know this time not how many moles, but how many molecules of H2O. But we can start in the same way. So we can start by calculating if hydrogen and oxygen, we want the molar mass of water. So it would be 2 hydrogens, 1 oxygen times 1.01 hydrogen, or the atomic mass of hydrogen, 16.00 for water, or for, sorry, oxygen. So 2.02, 16.00, we'll get 18.02 grams per mole water. So we do 3.64 grams. And again, we're going to divide by the grams of water and multiply by 1 mole of water. And then we have to add on one more step here and convert those moles into molecules. So we're going to have 1 mole is 6.022 times 10 to the 23 molecules. Molecules or atoms kind of works out the same. Or it does work out the same, I should say. So then, again, multiplying straight across the top here, 3.64 times 6.022 times 10 to the 23 divided by 18.02 will be 1.22 times 10 to the 23 molecules of water, or H2O. So we can take this a step further even, and we'll do this again in a few slides in a little bit. But how many atoms of hydrogen are there in this many molecules of water? If every molecule has 2 hydrogens, how many hydrogens are there in this many molecules? 2 times, yes, yeah. So it is just 2 times the number of molecules. So it'd be like 2.44 times 10 to the 23 atoms of hydrogen. So how many atoms of oxygen are there? So if it was 2 times this for hydrogen, it's just 1 times this for oxygen. So it is the same. So you don't need to multiply by 16. If we want to get to moles, then we could do that, or if we want to get to grams. But there are 1.22 times 10 to the 23 molecules of water. Every one of those molecules only has 1 oxygen. So we have 1.22 times 10 to the 23 atoms of oxygen. We'll come back to that. Oh, actually, it is the next slide. So it's like this, right? So if we have 3 leaf clovers, and you want to know how many leaves are on 14 clovers, it's 3 times 14, right? Because we have 3 on each of these clovers. So if we wanted to write this out a little bit more mathematically, though, we'd say we have 14 clovers, and we can use this 3 leaves to 1 clover as our conversion factor. And it can be, well, we want to cancel out clovers, and we have 3 leaves. 14 times 3 is 42 leaves. So it works the same way for molecules. Each molecule or formula unit tells you the number of each type of atom. So if you know the number of moles of the molecule, you can multiply that number of moles or number of molecules by the number of each type of atom, and you have that many of that atom. It's just like for spiders, every 1 spider has 8 legs. So if we had the horrible 1 mole of spiders, be too many spiders, we'd have 8 times that many legs. Ugh. Or 4 legs on 1 chair, or like we did in that previous one, 2 hydrogen atoms for every 1 water molecule. So we talked about mixtures and things, right? Mixtures, you can have variable proportions. For a molecular formula, though, these are fixed ratios. So every one of these, for this carbon tetrachloride, every carbon tetrachloride has 4 chlorines. There aren't any sad carbon tetrachlorides out there with 3 chlorines. They all have 4. If it had 3, then it'd be carbon trichloride. So using carbon dioxide here, there are 2 oxygen atoms per CO2 molecule. All right, so 2 oxygen atoms per CO2 molecule. If you had 2 dozen oxygen atoms, that means you'd only have 1 dozen CO2 molecules. Or if you have 2 moles of oxygen, then you only have 1 mole of carbon dioxide. Or vice versa, right? 1 mole of carbon dioxide, 2 moles of oxygen. So, number of moles of oxygen and 18 moles of CO2. What would be our ratio? Multiply by 2. Yeah, because there's two. You could write. Maybe I'll write it out here. We'll do, right? For every 1 CO2, we have 2 oxygens. So 1, and really you can insert here, right, whether that's molecules and atoms or moles and moles. If we have 1 mole of CO2, we have 2 moles of oxygen. So we'll have 36 moles of oxygen. We've been doing mostly whole numbers until this point, but it doesn't have to be. Works the same way. If we want to determine the number of moles of oxygen in 1.4 moles of sulfuric acid, what's the ratio of oxygen atoms to sulfuric acid molecules? For every 2 hydrogen, there are 4 oxygen, yeah. But what about for the sulfuric acid molecule as a whole?
You have to multiply 1.4 times 4?
Yeah, you do multiply 1.4 times 4, because we have, for every 1, let's just use moles of H2SO4. Right, that O4 means that there's 4 oxygens. So we'd have 4 moles of oxygen. So as a conversion factor then, we'll put 1 mole H2SO4. Right, since that matches 1 mole H2SO4, moles of H2SO4, 4 moles of oxygen. So we get 5.6 moles of oxygen. So it's always just the number of atoms is the ratio between that type of atom and the molecule. I think the only time that it gets a little bit more tricky is if you had something like calcium nitrate. Right? So if we wanted the ratio here of oxygen, the only thing that's more tricky about it is that you now have to multiply 2 by the number of moles, or the number of oxygen atoms inside here. So for every 1, say mole of calcium nitrate, we would have 6 moles of oxygen. So now we can finally answer that question from the very, very beginning. We can also calculate the number of carbon atoms inside of a human being. So if a mass of sodium chloride, or what mass of sodium chloride contains 2.4 grams of sodium? When I was explaining this to my Reedley College class last night, I think this problem really highlights the flexibility of being able to solve a word problem if you know how unit analysis works. So we don't really need to know conceptually how this works. We can say we're starting with grams of sodium, and we want to get to grams of sodium chloride. And really, based on the tools that we have available to us, the only thing we can do with grams of sodium is convert it to moles of sodium. So it's going to kind of combine actually everything that we've talked about already. So the molar mass of sodium is 22.99. 22.99. grams per mole sodium. So let's just do this. We'll convert 2.4. We want to go from grams to moles. So we'll put 22.99 at the bottom. That's 1 mole sodium. So now that we're at moles of sodium, we need to get from sodium to sodium chloride. So now we can use that ratio, like we were talking about with oxygens per sulfuric acid. How many sodium atoms are there per sodium chloride atom or molecule? 1. So it's just 1 to 1. So we can say, I'm going to run out of space. We have for every 1 mole of sodium, we need to have 1 mole of sodium chloride. And so it's a 1 to 1 ratio. So because we know that relationship, we can now convert between moles of sodium to moles of sodium chloride. So 1 mole of sodium is equal to 1 mole sodium chloride. So once we have moles of sodium chloride, how do we calculate grams? Do the mass of chlorine? Yeah, the molar mass of chlorine will help, which is 35.45. So this is where the molar mass of the compound is what we'll use. Since we have 1 sodium and 1 chlorine, we can just add those molar masses together. So 22.99 plus 35.45. Put it over here. So 58.44 grams per mole sodium chloride. So that'll let us convert now. Actually, I think the first time we're going from moles to grams. But we'll put 1 mole sodium chloride is 58.44 grams of sodium chloride. So just by following the units and the conversions available, we were able to convert 2.4 grams of sodium into grams of sodium chloride. And so what this is telling us actually is what the question's asking for. What mass of sodium chloride contains 2.4 grams of sodium? So 2.4, again, it's going to multiply across the top. So 2.4 times 58.44 divided by 22.99 will be 6.1 grams of sodium chloride. So you could eat 6.1 grams of table salt and be at the daily recommended limit for sodium. So we can determine the mass of oxygen in a 5.8 gram sample of sodium hydrogen carbonate, and we're given the formula here. So we're given the mass of the sodium hydrogen carbonate, right? Given 5.8 grams sodium hydrogen carbonate. This is one that was on the polyatomic ion, or was on the nomenclature worksheet that we didn't do. And then we want to find the mass of oxygen. So how many grams of oxygen? I think, and I noticed this, what problem was it? I think it was on the unit analysis worksheet, where there were some questions that have the information organized like this, where it says, determine the mass of oxygen in a 5.8 gram. And some people would go and say, oh, that's 5.8 grams of oxygen. When in reality, that's 5.8 gram sample of sodium hydrogen carbonate. So it's important to correctly identify where those numbers are actually associated, and not just using the fact that they're close together in the word problem. So we have 5.8 grams of sodium hydrogen carbonate, but we need to get to grams of oxygen. And a lot of this is going to be, all right, so I think I talked about this, like grams of A to moles of A to moles of B to grams of B. So in this case, A is our sodium hydrogen carbonate. So how can we get from grams of sodium hydrogen carbonate to moles of sodium hydrogen carbonate? Oh, 6.022 times 10 to the 23? That would be going from moles to atoms or moles to molecules. So here we have grams, and then we can use the molar mass of sodium hydrogen carbonate to go from grams to moles. And for that, we use all of the elements that we have here and their masses from the periodic table. So we can list these. We have sodium, hydrogen, carbon, oxygen. And then we just write down how many of each we have. So 1 sodium, 1 hydrogen, 1 carbon, 3 oxygens. Then we'll multiply each number of atoms by the mass, the molar mass of that atom, which we get from the atomic mass on the periodic table. For sodium, it's 22 point. Is that 3 nines or 2 nines? 22.98. Oh, it's 989. Yeah, so we'll do 99. And then hydrogen is 1.01. Carbon is 12.01. And oxygen is 16.00. Those are ones that I have memorized, but you can find their masses on the periodic table. And I am using just 2 decimal places. I'm using 2 decimal places because it takes up less space. On an exam, you should always use them all. So these ones that multiply by 1 are easy. 22.99, 1.01, 12.01, and then 16 times 3 equals 48. Yep, 48.00. So we can add all of those together now. 1.01 plus 22.99 and get 84.01. And the units of this, the units of all of these actually, are grams per mole of sodium hydrogen carbonate. So if we had 84 grams of sodium hydrogen carbonate, that would be 1 mole of those molecules. So we can use that now to convert. So we're going to have 5.8 grams, and since we want to get from grams of A to moles of A, we're going to divide by 84.01 grams of sodium hydrogen carbonate. And that'll give us moles of sodium hydrogen carbonate. So what would our next step be to go from moles of this to moles of that? What's the ratio of oxygen atoms to sodium hydrogen carbonate molecules? 1?
3 to 1.
3 to 1. Right, so it's just the number of oxygen atoms here. So there's 3 oxygen atoms in every sodium hydrogen carbonate. Just be on the lookout for when there are like parentheses. So if you had like 2 nitrate molecules or 2 carbonate molecules or polyatomic ions, then you have to multiply that 2 by everything inside of that. Something like calcium nitrate. So you'd have oxygens there would be 2 times that 3, so you'd have 6 oxygens. But for this one, it's just 3 moles of oxygen for every 1 mole NaCO3. And now, I've seen this in the past, and it does work out fine, but we're going to get the mass of now oxygen and use that to convert to grams of oxygen, right? The molar mass of oxygen, which is 16. We don't need to use the molar mass of 3 moles of oxygen, because I've seen that sometimes that there's 3 moles here, so you want to use 3 moles and cancel it out. But it's just 1 mole of oxygen, which is 16.00 grams of oxygen. What I mean when I say it works out is you could do, if you did 48.00 grams of oxygen is 3 moles of oxygen. The ratio between those is the same, right? So if you took 48 and divided by 3, it's 16 over 1. But you don't need to do that. You can do it this way. And now we just multiply across the top, divide by the bottom. So 5.8 grams times 3 times 16 divided by 84.01. You get 3.2 sig figs, 3 grams of oxygen. And then just a reminder on sig figs, because we're multiplying and dividing in this whole mess here, we just use the smallest number of sig figs, which is our 5.8. For the most part, and really, as I told you, you can ignore the sig figs of everything in here. This 3 to 1 is exact. Any questions there? For any of these, calculate the mass of something in something else. You're going to do this grams to moles to moles to grams that I had written up here. All right. Lots to cover. So, we've been talking about how the masses of the different atoms are different. And so you can't just looking at a molecule, say H2O, since it's the easy example, can't look at that and say, well, there's 2 hydrogens and 1 oxygen, so hydrogen's going to be 2/3 of the mass of water. It's not the case because hydrogen has an atomic mass of 1, whereas oxygen has an atomic mass of 16. What you can do, though, is use the percent mass of an element in a compound and use that to calculate how much there is of that compound in an element in a compound. So for this example, we have 0.358 grams of chromium reacting with oxygen to form 0.523 grams of the metal oxide. So the metal oxide is a very common problem. A metal oxide is going to be a compound of the metal, so in this case chromium, and oxygen. And so you'll have X number of chromiums, X number of oxygens. Don't know exactly what that ratio is. But we can use this formula. Say the mass of X in a sample of the compound. So here for this problem, X is our chromium. So it's going to be of 1 element in the compound. And then we can divide that by the mass of the sample of the compound. So the whole thing, in this case, the metal oxide. And then multiply by 100, and that'll give us the percent mass. So this will be, I'll do the 100 on this side. So 100 times 0.358 grams of chromium divided by 0.523 grams of oxygen, or metal oxide. Or I'm using X here to denote, we don't know how many of each. And percents are a pretty common thing that we use. And it's always just the portion, or the piece, divided by the whole. Will give you the percent of something. It's like the piece of the pie. So 0.358 divided by 0.523. And then we multiply by 100. And we'll get our mass of chromium is equal to 68.5%. And you would write this as chromium by mass. The other kind of problem that you'll commonly get here is that it'll ask you, what's the percent mass of the oxygen? And there's 2 ways you can do that. right? If we calculated and we know in this compound it's just chromium and oxygen, the other, 100 minus this percent of chromium will give us oxygen, right? That makes up the rest of the mass. The other thing you can do, and that's commonly what it's wanting you to think about, is if this is all chromium, 0.358 grams, it reacts with oxygen, and we get 0.523 grams. All of that mass came from oxygen being added to the compound. So if we do 0.523 grams minus our 3.5, oops, not 3.5. Eraser, please. There we go. 0.358 grams. That will give us the mass of oxygen that was added to the compound. So 0.523 minus 0.358. So we added 0.165 grams of oxygen. And we can use the same formula to calculate our percent mass of oxygen. Because sometimes it won't just be chromium and oxygen. There will be other things, so you can't just do the percent chromium and then get the rest of it as oxygen. So 0.165 now divided by 0.523 grams of the chromium oxide, or the metal oxide. And then times 100 will give us 31.5% oxygen by mass. And sure enough, in this case, the two of those together add up to 100. So both of those elements make up the whole thing. Any questions about percent mass? No?
The first number is always going to be on top when it comes to dividing. So you see how
When you're looking for percent mass, it'll be the smaller number. Yeah. You need to think about what it's asking too. So here, this says 0.358 grams of chromium, and then 0.52 grams of the metal oxide. So you're looking for the percent of that metal in the metal oxide. Because it could give you, I could write this problem as you have a sample of 0.523 grams of chromium oxide, and you started with this mass of chromium, right? What's the percent mass? So it won't always be the first number. It should always be a smaller number, because you can't have more than 100%. So sometimes it is easier to use percent mass as a conversion factor rather than using grams to moles to grams, right? We talked about like for mining, if you have ore, and you have a big chunk of ore, it would be easier to say that that's 50% iron and 50% other garbage rather than to do some other math, right? You get a 1 kilogram thing, that's 500 grams of iron, the rest is garbage. So one of the ways, I think there's a couple ways that you can think about this. I think the easiest one, to put it in terms of converting units like we've been doing, is if you think of the percent mass composition of sodium and sodium chloride. This is sodium in sodium chloride is 39%. You can just assume that we have 100 grams of sodium chloride. So then we have 39 grams of sodium in 100 grams of sodium chloride. And then when you look at this and say, okay, well, I've got, say, 36 grams of sodium chloride, how much sodium is in there? Well, if you're given 39%, you can change it into this type of conversion factor. And now we've got grams of sodium chloride and grams of sodium chloride, which will cancel out and give us grams of sodium. So 36 times 100, or sorry, times 39 divided by 100 is 14.04 grams of sodium. Of course, the other way that you can do this is just convert 39 to a proportion, right? Because we never use percents. We can convert this into a proportion. So if you had that same 36 grams of sodium chloride, and you said, I know that this is 39%, which 39 divided by 100 would give us 0.39. So 36 grams of sodium chloride times our 0.39. This is why I say it's easier to convert it into grams of sodium per grams of sodium chloride, because this is unitless. There's technically no units here, but this is representing the amount of sodium, or the proportion of sodium. And if we do 36 times 0.39, you get the exact same thing, 14.04, and this would be grams of sodium, because we started with grams of sodium chloride. This can be rewritten as not just grams, you can use any unit of mass there. So you could put kilograms per kilogram, grams per gram, you could use micrograms per microgram. I believe you could even use pounds per pound. Because we're dividing grams by grams, technically this is also unitless, but you can see the units to do the conversion. As long as it's the same units on the top and the bottom, it'll work. Oh, shouldn't hit the microphone. Is there any questions about this? Percent mass composition. Do you have a question? Do you have a question?
Yeah, where did you get the 36 from?
Oh, I made that up.
Oh, you did that.
Yeah, I was like, if you wanted to know in 36 grams of, yes. Right, 50 grams, 100 grams, 420 grams, whatever. Okay. We'll do some examples here, though. So if the FDA recommends you consume less than 2.4 grams of sodium per day, remember this is the same problem we did earlier, but before we used grams to moles and moles to grams. How many grams of sodium chloride can you consume and still be within the FDA guidelines? Again, sodium chloride is 39% sodium. And this is pretty key here, by mass. Right? So it tells you can use units of mass. So if we start...
We could just use any unit of mass, or like grams again?
Yeah, so you can use any units of mass. So if this said 2.4 kilograms, you would just rewrite this as 39 kilograms of sodium per 100 kilograms of sodium chloride. The key, of course, is to use, well, technically what you write there doesn't matter because it doesn't change any of the numbers, but you want to use units that match the units given in the problem. So in this case, we have 2.4 grams of sodium, and we're not going to use kilograms, we're just going to use grams.
So in the example, you specify kilograms or grams?
Yeah, if I had a problem like this, I would expect you to use, like I'll say like this, 2.4 grams of sodium, or 3.0 grams of sodium, or I would say kilograms. And so the units that you pick here just need to match in terms of canceling them out. So here, how do we want to arrange this? How do we want to orient our conversion factor? Yeah. So we want to match, we want to cancel out our units, right? So we want to put grams of sodium on the bottom. So it's 39 grams of sodium. And that means that we have 100 grams of sodium chloride on top. So then these cancel. And then we get 2.4 times 100 divided by 39. So this is 6.2 grams of sodium chloride. So you could eat 6.2 grams of table salt and still be within the FDA's guidelines. It's a lot of salt. It's a pile of salt. We can actually, if you wanted to for fun at home, this is a lab we do at Reedley College. They don't have set up here, where you take you measure out a mole of different things. So, right, you can calculate the mass of sodium chloride, mass of sodium, mass of chlorine, and then if you have a kitchen scale at home that has grams, or you can convert it to pounds or ounces or whatever, you could weigh out 1 mole of table salt, just to see what that looks like. And then Google the molar mass of table sugar and weigh out 1 mole of table sugar and see if those piles are different sizes. They will be. Okay. Any questions? Percent mass? Another conversion factor. So if a woman consumes 22 grams of sodium chloride, how much sodium does she consume? So the key here, this is right, sodium, and again, sodium chloride is 39% sodium by mass. So we're given 22 grams of sodium chloride this time. And we can use our same conversion factor, 39 grams of sodium per 100 grams of sodium chloride. And then we just line these units up. Because the units that we want to cancel will always go will go opposite, right? They'll be at a diagonal from each other, which is one of the things that I saw on the exam was if there were compound units, you have to convert both of those. So this will be 22 times 39 divided by 100. You get 8.6 grams of sodium. So it's like 3.5 times the daily recommended value of sodium. Which most things, I think, have the sodium listed in milligrams. So this would be 8,600 milligrams, or it should be 8.6 times 10 to the 3 milligrams of sodium. Should have looked up what's in a cup of noodles. It's probably like 2 grams of salt in every one of those. Any questions? Good. What?
I feel guilty now.
About eating cup of noodles? I always joke, my wife likes them. I mean, I like them, they're delicious, don't get me wrong. But I always feel like it's pretending to eat food, because I'm always hungry 10 minutes after I finish it. Just pretending. Okay, so that's when we're given percent mass, very easy to use that as a conversion factor. Right, you can kind of just pick the units there as long as they're units of mass. But we can also calculate mass percent composition from the chemical formula. So if you're given a chemical formula for something, you can calculate percent mass. And the key for this is finding the mass of 1 mole of the compound. So if you think about percentages, it doesn't matter how much you have of that substance. So for sodium chloride, if you have 10 grams of sodium chloride, that's still 39% sodium. If you have 1,000 grams, it's still 39%. So in this, we're picking 1 mole because it's easy to calculate, because those are all in grams per mole. And so then find the mass of 1 mole of the compound and the mass of the element in 1 mole of the compound. So we can take our mass of the element X in 1 mole of the compound and mass of 1 mole of the whole compound. So we'll do, let me just peek at, what's the example here? Oh yeah, that's a good one, okay. Just give you a little more time on that. All right. So if we have acetic acid, which is vinegar, calculate the mass percent composition of oxygen in acetic acid. I think problems like this can be intimidating because there are no numbers given, right? In some ways that can be intimidating. I think in other ways, though, it means that you can get those numbers from somewhere, right? Because you have to have numbers to be able to do the calculation. And in a problem like this, they're all going to come straight off the periodic table. So if we look back at this, we need the mass of 1 mole of the compound and the mass of the element in 1 mole of the compound. So those are going to be the molar masses, sometimes also called formula masses. So you have acetic acid, HC2, H3O2, which is going to be made up of hydrogen, carbon, and oxygen. And then we can just count the number of each of these. So hydrogen, right, there's 4 hydrogens. Even though they're spread out, this goes back to nomenclature. One of those hydrogens goes in front because this is an acid. But we still count that with the rest of the hydrogens. So there's 4 of those, 2 carbons, 2 oxygens. And now we just multiply by their masses, their molar masses, 1.01, 12.01, 16.00. Of course, these are all in grams per mole. And then we just multiply those. So 4.04, 24.02, and 32.00. And then we add them together. 4.04 plus 24.02 plus 32 is 60.06 grams per mole HC2H3O2. Okay, so that is the mass of 1 mole of the compound. So in our equation here, the mass of 1 mole of the compound goes in the denominator. And then, I guess, because this is 60.06 grams per mole, so 1 mole is going to be 60.06 grams. And always remember, it's always the part divided by the whole. So our whole thing here is the compound, acetic acid. So what is the mass of our oxygen? 32, right? So the nice thing about doing our compound first is that along the way we calculate that anyway. So we can plug in 32.00 grams of oxygen. So we'll divide those, multiply by 100. 32 divided by 60.06 times 100. So we have 4 sig figs. So 53.28%, and this should be oxygen by mass. Because you can also do things by volume, but we're not doing that here. So it's important to write by mass. So you could do this for any compound. If you know the whole formula, you could do this for any compound, right? We could now calculate the percent mass. Actually, let's do that really quickly. So if we calculate the percent mass of these other things, so how much hydrogen, this will be a good sort of check. And then how much carbon, so 24.02 divided by 60.06. If we get the percent mass of all of these, when you add those together, they should add up to 100, because that is all of the mass. So 4.04 divided by 60.06 is times 100 is 6.727% hydrogen. 24.02 divided by 60.06 is 39.99% carbon. So 53.28 plus 6.727 plus 39.99, probably going to be close. Yeah, not 100%, but 99 point, well, with sig figs it is 99.997%. That's more than close enough to call that rounding error. Right, so the masses of all of those together, 100%. That's the whole compound. And yeah, you could do this for anything. All right, so our mass percent composition can be calculated from a chemical formula. Conversely, we can also calculate a chemical formula from mass percent composition. So if you have the masses, the mass percent of each of the constituent elements, like our previous example, hydrogen, carbon, and oxygen, then you can calculate a formula mass. And we talked about formula mass before. And it's the simplest whole number ratio of the elements. So derived from or guided by experience or experiment. You guys will do a lab on that, maybe even next week. So the empirical formula gives only the smallest whole number ratio of each type of atom, not the specific number. The molecular formula then is always a whole number multiple of the empirical formula. So if you get an empirical formula, the molecular formula sometimes is the same, but sometimes it'll be 2 times bigger, or 3 times bigger, or 4 times bigger. It'll always be some whole number multiple though. For example, hydrogen peroxide, the empirical formula is hydrogen and oxygen, but the molecular formula is that really times 2, H2O2. I do remember this, well, yeah, I remember these problems were hard for me. But there's one very specific key thing. So if we have a sample of water decomposed in the laboratory, so this is an experiment I think I've told you about. You can, they're using a 6-volt battery here, but you can also use a 9-volt battery. If you want to collect things, it's better to use wires, but you can drop a 9-volt battery into salt water, and it'll start splitting water into hydrogen and oxygen. Hydrogen at one terminal, oxygen at the other. So if we have 3 grams of hydrogen and 24 grams of oxygen, 3.0 grams hydrogen, 24 grams of oxygen. The empirical formula is the whole number ratio of the atoms. We know that the masses, aside from using molar masses, don't really tell us anything about the number of atoms, right? Because they all have different masses. So to determine the empirical formula, we just convert these to moles. And then the empirical formula is the ratio between the types of atoms. So 3 grams of hydrogen, we'll use its molar mass of 1.01 grams hydrogen for 1 mole hydrogen. And for oxygen, 16.00 grams oxygen for 1 mole oxygen. So 3 divided by 1.01, should be no surprise that it's very close, 2.97, so we can round that up to 3. All right, with the correct number of sig figs, 3.0 moles of hydrogen. And And then for oxygen, it'll be 24 divided by 16, which is exactly 1.5 moles of oxygen. Now, if we want to find the ratio between all of these, we just divide all of them by the smallest number of moles. So this will be 3 moles divided by 1.5, and 1.5 divided by 1.5. I'm actually going to erase this. So then this is 2 moles of hydrogen for every 1 mole of oxygen. And as we know, the formula for water is H2O. So this is one of those cases where you do this experiment, get the empirical formula as well as the molecular formula. Do the written out rules here. So it won't always be as clean as that, right? Because that, even the 3 rounded up to 3.0, it's not always that clean. Especially for your experiment, it won't be that clean. So we start with the masses of each element present in the sample of the compound. Right? So we started with 3 grams of hydrogen, 24 grams of oxygen. Okay, so start with masses, then convert each mass to moles using molar mass as a conversion factor. Because they're in grams, convert them to moles. Then we divide all of the moles by the smallest number of moles. So we took 3 divided by 1.5, took 1.5 divided by 1.5. Then after that, if you don't get whole numbers or really close to whole numbers, for really close I mean like within 0.05, then you have to multiply all the moles to get whole numbers. And that's what this chart is here. So if you divide all of them by the smallest number and you get one of them has 0.33, then you have to multiply all of them by 3 to give you whole numbers for everything. Because you can't have 1/3 of an atom or half of an atom. And then you take those numbers, the number of moles of each in that ratio, and you write them, you write the formula using the numbers of moles as subscripts. So first you start with grams, convert everything to moles. Divide by the smallest number of moles. Check if your whole numbers, if you have whole numbers there, really close to whole numbers. Multiply if you have to by a factor here to get whole numbers. Then use those numbers as the subscripts in the formula. What was the other one that's like this? Because there have been a few other slides. These are like really good slides to just have on hand or write on a cheat sheet for an exam. Okay, so we're going to apply this all. Oh, that's right. It's right here. Okay, so now with all of the steps in mind, though, we can start with the grams of each of these. 3.0 grams, 24 grams of oxygen. And then step 2 is convert to moles. So use the molar mass, grams of hydrogen, 1 mole of hydrogen, 16.00 grams of oxygen, 1 mole of oxygen. Should have these in my calculator already. Oh, that's right, because this came out to, with the correct number of sig figs, 3.0, and this was exactly 1.5. Okay, so now we have the moles of each. We just divide everything now by the smallest number of moles. So divide by 1.5, divide by 1.5, and this will be 2 moles of hydrogen, 1 mole of oxygen. And now we write our formula. Well, actually, here we check, right? We got whole numbers. Always nice. We're going to have hydrogen and oxygen. And now we use those number of moles that we got here at the end as the subscripts in our formula. So H2O1, but we leave the 1 off because it's implied. Cool. Any questions? These weren't the problems that I found hard. I think it's this next one. No, not this one. So you can combine this with percent mass. But we'll get there. It's not that hard. There's a trick. There it goes. Took long enough. All right. So it's the same procedure, except now we have 3 different kinds of elements. Actually, we're just going to have a bunch of these examples back to back to back. So we're going to have 165 grams of carbon, 27.8 grams of hydrogen, 220.2 grams of oxygen. So what's our first step? Or second step, I should say. Get the molar masses, convert to moles. Yeah. So carbon is 12.01, 1.01, and 16.00. Whoops. Oxygen. I would really encourage you to write these units in every time. As much of a pain as it is, does help keep you from getting lost. Okay, so 165. 165 divided by 12.01. 13 point. I'm going to write out in excess of numbers here. $27.525. This is going to be 13.76. Stop at 3. So moles of carbon, moles of hydrogen, moles of oxygen. All right. So what's the next step? Divide by the smallest one. Which one's the smallest one?
13.73.
Yeah. Now, here's another question. Do you think it matters?
No.
They're close enough. In this case, it doesn't really matter. You can just do either of them, but we'll do the smaller one. And I know that sometimes, because I remember this was at some point, I had a hard time with, deciding which decimal is smaller at a glance. If you subtract one from the other, if you get a negative number, the first number is smaller. So if we do 13.739 minus 13.763, it's negative 0.024. So that means that this one is smaller, even if by a tiny amount, than the other one. So we'll divide everything by 13.739. 13.739. So this first one will be exactly 1. And the second one will be, so 27.525 divided by 13.739. 2. It's 2.003. So I'm just going to write 2 moles. And then our last one is going to be very, very close to 1. So 1.0017. So 1 mole of oxygen. And here, Because these are mole ratios of the individual elements, we can't have fractions, right? So it doesn't make sense here, even though the sig figs would say that we need to have, right, 3 sig figs on each of these. We can't have, if it was 1.00 or 1.01, isn't how it works. That's actually just experimental error or rounding error or error from somewhere. So in this case, we can just write the single digit, which you should get single whole digits. Oh, the caveat being, if it is one of those in-between fractions. So here, they were all very, very close to being whole numbers. If it was closer to 0.1 than it was to 0.0, then write that 0.1, because it's going to be important to multiply by 10. So if you get a number that's in between, you need to write those out. And I think the next example will have that. All right, so now we can write, we have carbon, hydrogen, oxygen. Oh, just remember, there are those rules from like I think they're chapter 5 actually, for the order that the elements go in. And I think this is right, but so this will be, we just use these subscripts now. Actually, I'll write these in. So 1, 2, and 1. So your final answer, because the 1s are implied, should be carbon, 2 hydrogens, 1 oxygen. And that's our empirical formula. Any questions? No? All right. All right. These are the problems. This type of problem, initially, I found difficult. But this is one of those things that I remember as an aha moment. So if we have these percentages, remember I told you you could just treat this as like 75.69 grams of carbon per 100 grams of, in this case, ibuprofen. We can do that again here. So we're going to do that, but we're also going to assume that we have 100 grams of ibuprofen. So if we start with, let me do it like this actually. So we have 100 grams. I'm just going to write IB for ibuprofen. And again, we need to get the masses of each thing first. So we're given percents. So 100 grams of ibuprofen times 75.69 grams of carbon per 100 grams of ibuprofen. It's just going to be 75.69 grams of carbon. So for problems like this, where you're asked to calculate the empirical formula for mass composition, percent mass composition, assume 100 grams. And then because of this math, you can just rewrite the percentage as the number of grams. Because kind of like how the percentage doesn't change based on the amount of ibuprofen you have, the chemical formula doesn't change either. Right, it's independent of the amount. So I'll write these all out this way though. 100 grams of ibuprofen times 8.80 grams of hydrogen per 100 grams of hydrogen. Ibuprofen. 100 grams of ibuprofen again times 15.51 grams of oxygen. So I don't expect you to write this initial step out, honestly. I would not mind if you just jumped straight to the grams. All right, so that is like the one thing for these problems. Just assume that you have 100 grams, because it makes everything easier. You could assume that you had any amount. You will still get the right answer, but 100 grams makes it really easy. All right, so our next step, just as with the other problems, is we're going to convert to moles. Actually, I'm going to make this I'm going to run out of space. All right, so grams of oxygen, grams of hydrogen, grams of carbon. These are all 1 mole. Again, because the molar mass is the grams per mole. So 75.69 divided by 12.01 is 6.3022 moles of carbon. 8.80 divided by 1.01. 8.7129 moles of hydrogen. And then 15.51 divided by 16 will be 0.969. Let's do 4 moles of oxygen. Then we just divide by the smallest number of moles. I'm going to write it this way this time. These are the kind of problems that have so many steps that when I do them on the board or do them on the projector, it seems really easy to remember all the steps. So definitely these are great candidates for going back to the blank slides, trying to do the problems yourself without looking at notes or just using maybe the steps. I would try it without notes first, see how far you get. Then take a glance at the steps, then go back to trying to do it. Because really the only way you can test what you know is if you rely only on what you know. Because I remember so many times thinking like, oh yeah, I looked over the notes, I'm good for this test, no big deal, get to the test, I didn't know anything. Okay, so this is 501, 8.7129, 0.9694. This is 8. 8. And then, oh, this is. So on the previous one, I just rounded them, right? So on this one, I wanted to write out some more of these decimals, especially since like this one's not as close as the other ones that we saw. But this is a good example of it's still really close. And if you wanted to maybe look at this a little more easily, again, you could say, all right, this is really close to 9. I want to know how close it is to 9. So you can do 9 minus 8.988. And you'll see that it's, whoops. Oh, I typed that wrong. 8.988. And that's 0.012. So going back to over here, is that updated up there, right? So 0.1 is the smallest sort of difference that we would look at and say we need to multiply this by something to get a whole number. But we are not at 0.1, we are at 0.01. So I would say if you're like only 0.07, 0.08 away, then maybe you would round to that 0.1. In this case, though, we can just call this one 9. We're close enough to 9 to say this is 9. But this one is 6.5. So we are going to have to multiply everything by a factor to get whole numbers in this case. And it did still completely run out of space. So if we have carbon, hydrogen, oxygen, with how do I want to do this? So the factor we can go back to that chart, but we're going to multiply by 2. We're going to multiply this by 2, and multiply this by 2. So our final numbers will be, in super cramped space, 13 moles of carbon, 18 moles of hydrogen, and 2 moles of oxygen. So this is going to be carbon, hydrogen, oxygen, and we're going to have 13, 18, and 2.
You got the times 2 from where again?
So times 2 is because we have to multiply 6.5 times 2 to get a whole number. Mm-hmm. Yeah. So it is, the number of times that you have to multiply to get a whole number. So if you had 0.33, you have to multiply that by 3 to get a whole number. So if you had 0.33, you have to multiply this by 3. It'll give you 0.99, essentially 1. Right, so you multiply everything by that factor. So because 6.5, you have to multiply it by 2 to get a whole number, which is what this previous chart is for. All right, so here we're at 0.5, so we multiply by 2. Yeah?
Will we get that on the test, or will we have to write that down?
You have to write that down.
Okay.
The other way to check, the other way you can do this is, this is 1 divided by 10. This is 1/5. This is 1/4. This is 1/3. That's 1/2. That's 2/3, and then 3/4. So you have to multiply by the denominator on those to get whole numbers. You could do it trial and error too, right? You can take that number, multiply by 2, multiply by 3, multiply by 4, until you get there. Shoot. I'll just all right, we're gonna skip this one because you'll do that one in a lab. We'll cover it there. So the molecular formula, though, we talked about this. Molecular formula is always a multiple of the empirical formula. Sometimes it's 1, but sometimes it's 2 or 3 or 4. It's always a whole number multiple. And so you can calculate or figure out what that multiple is, n in this case, by taking the molar mass of the compound, dividing it by the empirical formula molar mass. And then you multiply all the subscripts in the empirical formula by n to arrive at the molecular formula. I think this is there are 2 here. So if the empirical formula for fructose is, right, empirical formula, carbon, hydrogen, oxygen. So we can calculate the formula mass for this as 1, 2, and 1 times 1.01, 12.01 times 16.00. So it'll be 12.01, 2.02, and 16.00. So this will be 3.003. So this is the molar mass of our empirical formula. So then the molecular formula is going to be the CH2O. We're going to multiply all of those subscripts by some factor n. The way we get n is we take our 30.03 grams per mole of the empirical formula and divide by, oh no, sorry, did that backwards. It's 180.2 is the molecular formula divided by 30.03, which I believe is 60 or 6. So 80.2 divided by 30.03, yeah, is 6. So this 6 equals N. So if we take CH2O, multiply those subscripts by 6, we'll get C6H12O6. So to calculate, to get this molecular formula, you have to be given the molar mass of the molecular formula or the factor to multiply by. Otherwise, you can't calculate it. Yeah, so this is the last one. We'll do this one. I'll say for that one that I did skip, go back. It uses the thing that I talked about with metal oxides. It's that same kind of problem. But butane in this example is a compound containing carbon and hydrogen used as a fuel in butane lighters. The empirical formula is C2H5, and its molar mass is 58.12. So we're going to do, 2 of those, 5 of these, multiply by their molar mass. So we're going to get 24.02, 5.05, so this will be 29.07. And this again is the empirical formula, molar mass, goodness gracious. So then we'll have, it's always going to be a whole number. So we're always going to have the larger number divided by the smaller number when calculating this ratio. So this will be 58, which is the molar mass of the compound, 58.12, divided by our 29.07. Which I'll bet you it's going to be 2. 58.12 divided by 29.07 will give us 1.9993. It's close enough. Again, this is one of those things that we're using as a factor, as a whole number. So we need to get that whole number factor. So it's going to be 2. And then we take our empirical formula, C2, H5. We're going to multiply all of the subscripts by 2 to get C4, H10.